Welcome to DAR Tutors. In this video, we'll explore complex numbers, focusing on concepts crucial for the IB mathematics, applications and interpretation higher-level curriculum. Our main objective is to understand how complex numbers, often expressed in the form z equals a plus bi, can be visualized and manipulated geometrically. We'll begin with the Argand diagram and use it to explain a key property, the conjugate of a sum. We represent a complex number, z equals a plus bii, as a point P with coordinates, AB on a plane called the Argand diagram. The horizontal axis is the real axis, and the vertical is the imaginary axis. The complex conjugate of z, denoted z star, is formed by changing the sign of the imaginary part. So if z is a plus bi, z star is a minus bi. Geometrically, this means z star is a reflection of z in the real axis. Now, let's explore a key property. For any two complex numbers, z and w, the conjugate of their sum is the sum of their conjugates. That is, the quantity z plus w, all conjugated, equals z star plus w star. Let's prove this algebraically. Let's define our two complex numbers. Z equals a plus b, and w equals c plus d. First, we find their sum. Z plus w equals a plus c plus I times b plus d. Next, we take the conjugate of the sum. This means we change the sign of its imaginary part. So, the conjugate of z plus w is a plus c minus I times b plus d. Now let's calculate the right side of the equation. We find the conjugates of z and w separately. Z star is a minus bi, and w star is c minus di. Their sum, z star plus w star, is a plus c minus I times b plus d. Notice that this result is exactly the same as the conjugate of z plus w that we found earlier. We have shown algebraically that is z plus w, z plus ww. The same logic applies to subtraction. W. This property simplifies many operations with complex numbers. Let's apply this to a concrete example from your notes. Consider the complex numbers z equals 2 plus 3 and w equals negative 3 minus I. Let's illustrate these on an Argand diagram. S corresponds to the vector from the origin to the point, 2, 3. U corresponds to the vector from the origin to 3, 1. The problem asks us to find the product z y. We multiply the two complex numbers. S times w equals 2 plus 3i times as negative 3 minus I. Using the distributive property, or FOIL, we get negative 6 minus 2i minus 9i minus 3i squared. Remember, I squared is negative 1. Substituting e squared equals negative 1, we get negative 6 minus 11i plus 3. Combining the real parts, we find that the product zo is negative 3 minus 11i. Now, let's represent this product on our Argand diagram. The product ZW corresponds to the vector from the origin to the point, 3, 11. This visual confirms our calculation. This example reinforces our ability to perform complex multiplication and visualize the result. We have now seen how to plot complex numbers and their product on an Argand diagram. We've established that the Argand plane is like a vector space. Just as vectors have magnitude and direction, so do complex numbers. The magnitude of a complex number is called its modulus, and its direction is called its argument. Let's formalize these definitions. The modulus of a complex number z equals a plus bi, denoted with vertical bars, is the distance from the origin to the point a, b. By the Pythagorean theorem, this length is the square root of a squared plus b squared. The argument of z, written as arg z, is the angle theta in radians, measured counterclockwise from the positive real axis to the vector representing z. For uniqueness, we restrict theta to the interval from negative pi non-inclusive to pi inclusive. For purely real numbers, z equals a. The argument is either 0 if a is positive, or pi if a is negative. For purely imaginary numbers, z equals bi. The argument is pi over 2 if b is positive or negative pi over 2 if b is negative. These two components, modulus and argument, allow us to fully describe any complex number and form the basis for another representation known as polar form. Let's work through an example to find the modulus and argument of a complex number in the fourth quadrant. Consider the complex number z equals 1 minus I. Our objective is to find its modulus and its principal argument. First, the modulus. Using the formula z equals the square root of 1 squared plus negative 1 squared, which is the square root of 2. So the distance from the origin to the point 1 to 1 is root 2. For the argument, we visualize the number. It's in the fourth quadrant. The tangent of the angle theta is the imaginary part over the real part, which is 1 over 1, or 1. To find the angle in the correct quadrant, we can use a reference angle, phi, in the first quadrant, where tan phi equals the absolute value of the ratio. The reference angle phi, where tan phi equals 1, is pi over 4 radians. Since our number is in the fourth quadrant, we measure clockwise from the positive real axis. Therefore, the argument theta is negative pi over 4. So, for the complex number z equals 1 minus I, the modulus is root 2, and the argument is negative pi over 4. Understanding how to find the argument in each quadrant is essential. Let's briefly recap. In the first quadrant, the argument is simply the reference angle phi. In the second, it's pi minus phi. In the third, it's negative pi plus phi. And in the fourth, it's negative phi. Now we'll investigate a key geometric locus on the Argand plane, the circle. Our goal is to connect the modulus of a complex number with the geometric definition of a circle. A locus is simply a set of points that satisfy a certain condition. Let's consider the equation modulus of z minus c equals r. The term ci represents the distance between 2 points. Let z be the complex number a plus bi, corresponding to point P, A, B, and let C be the complex number D plus I, corresponding to point Q, D, E. Then the modulus of Z minus C is the distance between the point P and the point Q. So the equation tla E S E equals R states that the distance from point P to point Q is always R. This is precisely the definition of a circle. The point C is the center, and the constant R is the radius. So, the locus of all complex numbers z that satisfy this equation is a circle with center C and radius r. Let's work through an example. Illustrate the locus of points that satisfy the equation modulus of z minus I equals 2. By comparing this to our general form, equals ci equals r, we can identify the center and radius. The center C is I, which is the point 0, 1 on the Argand plane. The radius r is 2. Therefore, the locus of points is a circle centered at 0, 1 with a radius of 2. We can sketch this on the Argand diagram. We plot the center at 0, 1 on the imaginary axis, and then draw a circle with a radius of 2 units around it. This circle contains all possible values of z that are 2 units away from I. We have now learned how to determine and sketch a circular locus on the Argand diagram from an equation involving the modulus. There are other important geometric loci as well. Let's look at one that doesn't form a curve, but a straight line. Consider the equation modulus of z minus c. 1 equals modulus of z minus c2. Here c1 and c2 are distinct complex numbers. Let's interpret this geometrically. It means the distance from a point z to the point c, 1 is equal to the distance from z to the point c2. The set of all points that are equidistant from 2 fixed points forms a straight line. Specifically, it forms the perpendicular bisector of the line segment connecting those 2 fixed points. So, the perpendicular bisector of the line segment connecting C1 and C2 is another important locus on the Argand plane. Let's illustrate the locus for the equation modulus of z equals modulus of z plus 4. First, we rewrite the right side to match our standard form z minus c. The equation is equivalent to modulus of z minus 0 equals modulus of z minus negative 4. This tells us the locus is the set of points equidistant from 0 and 4. The 2 fixed points are the origin 0, 0 and the point or 4, 0 on the real axis. The midpoint of the segment connecting 0, 0 and 4, 0 is phi 2, 0. The line perpendicular to the real axis at this point is a vertical line passing through x equals 2. This is the perpendicular bisector. So the locus of points satisfying 4 is the line x equals 2. Every point on this line is the same distance from the origin and from the point 4, 0. So far, we've explored complex numbers using their Cartesian or rectangular form z equals a plus bi. We also defined the modulus and argument, which are a complex number's inherent length and direction. These two components give rise to an alternative, and often more convenient way of writing complex numbers, the polar form. The polar form expresses a complex number z using its modulus, which we'll call r, and its argument theta. From trigonometry in a right-angled triangle, we know that a, the adjacent side, is r times cosine of theta, and b, the opposite side, is r times sine of theta. By substituting these back into the Cartesian form, we get z equals r e t cos theta plus I times r sin theta. Factoring out r gives us r times cos theta plus I sin theta. This is the polar form. For simplicity, we use the shorthand cis theta, which stands for cosine e sine. So, the polar form is often written as z equals r cis theta. One of the most powerful reasons to use polar form is how it simplifies multiplication and division. Let z1 be r1 cis theta 1 and z2 be r2 cis theta 2. The product z1 z2 is r1 times r2 multiplied by cis of theta 1 plus theta 2. This means you multiply the moduli and add the arguments. Division is similar. The quotient z1 over z2 is r1 over r2, cis of theta 1 minus theta 2. For division, you divide the moduli and subtract the arguments. This remarkable property is a cornerstone of complex number theory, allowing us to think of complex multiplication as a combination of a scaling and a rotation. Let's work through an example of complex multiplication using polar form. This illustrates how to convert to polar form, multiply, and convert back to Cartesian form to verify the answer. The problem is to find the exact value of the product, square root of 3 plus I times negative 1 plus I, using polar form. Let's first convert both numbers, which we'll call z1 and z2, to polar form. Let's 1 equal root 3 plus I. It's in the first quadrant. Let's find its modulus. It's the square root of root 3 squared plus 1 squared, which is 2. The argument is arctan of 1 over root 3, which is pi over 6 radians. So, z1 is 2 cis pi over 6. Now for z2. z2 equals negative 1 plus I. This number is in the second quadrant. Its modulus is root 2. The reference angle is pi over 4, and since it's in the second quadrant, the argument is pi minus pi over 4, which is 3 pi over 4. So, z2 is root 2 cis 3 pi over 4. Now we multiply them in polar form. We multiply the moduli and add the arguments. The new modulus is 2 root 2. The new argument is the sum of pi over 6 and 3 pi over 4, which simplifies to 11 pi over 12. So, z2 is 2 root 2 cis 11 pi over 12. To verify, let's also do this in Cartesian form. Root 3 plus I times negative 1 plus I is negative root 3 plus I root 3 minus I squared. This simplifies to negative root 3 plus 1 plus I times root 3 minus 1. These two forms are equivalent. While the Cartesian form here looks more complex, the polar form multiplication was very straightforward. This highlights the power of polar representation for these operations. Now, let's explore a very useful transformation: multiplication by I. Geometrically, what does this operation do to a complex number? Our objective is to prove that multiplying by I is equivalent to an anti-clockwise rotation of 90 degrees. We can prove this using two methods: Cartesian algebra and polar form. First, the Cartesian method. Let's take an arbitrary complex number z equals x plus iy. Multiplying by I, we get i's equals I times x plus iy, which equals xi plus I squared y. Since I squared is negative 1, is simplifies to negative y plus xi. So a point P with coordinates xy is mapped to a new point P prime with coordinates y, x. Let's see what happens to the length and angle. The modulus of z is the square root of x squared plus y squared. The modulus of z is the square root of negative y squared plus x squared, which is the same as the modulus of z. The length doesn't change. For the angle, notice that the original slope was y at x and the new slope is x y. These are negative reciprocals, which means the lines are perpendicular. A rotation that preserves distance and creates a perpendicular angle is a 90-degree rotation. Since our new x-coordinate, y, is the negative of the original y, the rotation is anti-clockwise. We can confirm this beautifully with polar form. Let's write z and I in polar form. Now we multiply. We multiply the moduli and add the arguments. R times 1 is r, theta plus pi over 2. The result is a complex number with the same modulus r, but its argument is pi over 2, or 90 degrees, greater than the original argument. This confirms that multiplying by I is equivalent to an anti-clockwise rotation of 90 degrees. So far, we've seen Cartesian form and polar form. Now we'll introduce the third and most elegant form, Euler's exponential form. This form is built on one of the most famous and profound identities in mathematics. It's called Euler's formula. For any real number theta, e to the power of e theta equals cosine theta plus I sine theta. This single equation connects 5 fundamental constants of mathematics: e, I, pi, 1, and 0, in a special case when theta is pi. When theta is pi, Euler's formula becomes e to the I pi equals -1. This form is incredibly useful in applied mathematics, engineering, and physics because it connects exponential growth and periodic oscillation. Since we know polar form is z equals r cis theta, we can replace cis theta with e to the I theta. This gives us the exponential form, z equals r times e to the I theta. Let's work through an example from your notes to convert between forms. Suppose we have the complex number z equals 4 times e to the power of -0.7. By comparing this to the general form re to the I theta, we can immediately identify the modulus and argument. The modulus r is 4, and the argument theta is -0.7 radians. Now let's find the Cartesian form, x plus ye. We use Euler's formula. 4 times cos of -0.7 plus I sine of -0.7. Using a calculator, we find that cos of 0.7 is approximately 0.7648, and sin of 0.7 is approximately 0.6442. Plugging these values in, z is approximately 4 times 0.7648 minus 0.6442i. Distributing the 4, we get the Cartesian form, approximately 3.0592 minus 2.576i. This shows how to easily extract information and convert between the exponential and Cartesian forms. Euler's formula provides a powerful tool for manipulating exponential expressions that involve complex numbers. This allows us to connect complex numbers back to the physical world, for example, in the study of waves. Let's investigate how complex exponentials can be used to add trigonometric functions of the same frequency but different phases. This technique is often used in fields like electrical engineering and physics. The key insight is to recognize that a cosine function can be represented as the real part of a complex exponential. Using Euler's formula, e to the I theta equals cos theta plus I sin theta, the real part is simply cosine theta. The problem we'll solve is to write the sum of 2 cosine waves in the form of a single cosine wave. We need to rewrite 10t cos 2t plus 1 plus 7 cos 2t plus 3 in the form a cos 2t plus b. Here 2d represents the common frequency. Step 1. Express the sum of cosines as the real part of a sum of complex exponentials. The sum is the real part of 10e to the I 2t plus 1 plus a 7e to the I 2t plus 3. Step 2. Simplify the expression inside the parenthesis by factoring out the common e to the I 2t term. This gives us e to the I 2t, multiplied by the sum of 2 constants, 10 ahal sin e to the I and 7 sha 7e to the I3. The second term is our phase-shifted component. Step 3. Evaluate the constant part of the expression. We can do this using a calculator. Let's find the value of 10t and cheapo e to the I plus 7e to the I3. This represents a complex number that combines the 2 phase shifts. A calculator gives us approximately 1.553 plus 9.4 EI. Step 4. Convert this complex constant back into polar form. This will give us our amplitude A and phase B. Converting 1.53 plus 9.40 I to polar form, we find the modulus A is about 9.53 and the argument B is about 173 radians. Step 5. Substitute this back into the original expression. The expression becomes the real part of e to the I2t times 9.53 e to the I1.73. We can combine these exponentials by adding the powers. Then we take the real part, which gives us our final answer. So we have successfully combined the two cosine waves into a single wave with amplitude 9.53 and phase shift 1.73. We've shown how the exponential form provides a powerful method for solving this type of problem. Let's work through another application example similar to exercise 11J to further illustrate how the exponential form can be used in the physical sciences. Consider two voltage sources in a circuit. One provides V sub A equals 20t cos 3t volts, and the other provides V sub B equals 30 cos 3t plus pi 4 volts. We want to find the total voltage, V sub t, in the form A cos 3t plus B. Again, the strategy is to move from trigonometry to the complex plane. The total voltage is the sum of the real parts of the corresponding complex exponentials. Factor out the common time-dependent term e to the I3t. We get the real part of e to the I3t times the constant term, which is the sum of 20 and 30t e to the IPI over 4. Now we'll evaluate this constant term. Remember, e to the IPI over 4 is cis pi over 4, so the constant is 20 plus 30 times cos pi over 4 plus I sin pi over 4. We know that cos pi over 4 and sin pi over 4 are both 1 over root 2. Plugging this in, we get 20 plus 30 over root 2 plus I times 30 over root 2. Now we need to find the modulus and argument of this complex number. The modulus will be our amplitude A, and the argument will be our phase B. Let's use a calculator to find the polar form of this complex number. The modulus A is found to be approximately 46.85, and the argument B is approximately 0.54 radians. So the total voltage is approximately 46.85 times cos 3 plus 0.54. We've successfully combined the two sources into one. We can see that the maximum voltage, which is the amplitude A, is approximately 46.85 volts. This is higher than the individual maximums of 20 and 30 volts, due to the constructive interference of the two waves. Let's work through another problem to ensure full understanding. We'll find the modulus and argument of a value derived from z. Suppose we have a complex number z with modulus 3 and argument theta, where theta is acute. That means theta is between 0 and pi over 2. Find the modulus and argument of z over 1 minus I. To solve this, we'll first express everything in polar form. We're already given z in polar form as 3 cis theta. Now, let's find the polar form of the denominator, 1 minus I. We've seen this before. The modulus is root 2, and since it's in the fourth quadrant, the argument is negative pi over 4. Now we can write the expression in polar form. It's 3 cis theta divided by root 2 cis negative pi over 4. We use the division rule for polar forms. Divide the moduli and subtract the arguments. The new modulus is 3 over root 2. The new argument is theta minus negative pi over 4, which is theta plus pi over 4. Let's just quickly check that this argument is in the principal range. Since theta is between 0 and pi over 2, the argument theta plus pi over 4 must be between pi over 4 and 3 pi over 4. This is within our range of negative pi to pi. So, our final answer for the modulus is 3 over root 2, and the argument is theta plus pi over 4. Notice that we've found the result in terms of the given variable theta. This example shows how polar form allows us to simplify complex expressions involving division and also to work with angles in the principal argument range. As a valued viewer, we want to share that DAR Tutors offers expert personalized online and home tuition for IB, A-Level, and IGCSE mathematics. Our experienced teachers are dedicated to helping you achieve your academic goals and master even the most challenging topics. If you're looking for support that goes beyond what this video can offer, we invite you to contact DAR Tutors today. We can provide tailored lessons and guidance to help you excel. Visit our website or use the contact information on screen to learn more. Let's conclude this session by working through some IB-style practice questions to solidify your understanding. First, let's look at this problem. A regular hexagon ABCDEF is centered at the origin O on an Argand diagram, with vertex A at 2. We need to find the modulus and argument of the vector representing A minus C. Since it's a regular hexagon centered at the origin, the vertices lie on a circle. The position of A is the complex number z sub A equals 2. This means the circle has a radius of 2. The vertices are spaced at equal angles. A full circle is 2 pi, so each angle is 2 pi divided by 6, which is pi over 3. The vertices are spaced at angles of pi over 3. C is the third vertex, so its argument is 2 pi over 3. Therefore, the complex number for C is 2 cis 2 pi over 3, which in Cartesian form is 1 plus I root 3. Now we can find A minus C. This is 2 minus our 1 plus I root 3, which equals 3 minus I root 3. First, the modulus. It's the square root of 3 squared plus negative root 3 squared, which simplifies to the square root of 12 or 2 root 3. For the argument, the number is in the fourth quadrant. The tangent of the reference angle phi is root 3 over 3, so phi is pi over 6. The argument theta is negative phi, or negative pi over 6. So the vector A minus C has a modulus of 2 root 3 and an argument of negative pi over 6. Next question. We are given the identity e to the IPI over 7 plus root 2 times e to the negative IPI over 4 equals e to the IPI over 5. We need to find the exact values of the real numbers a and b. The strategy here is to expand everything using Euler's formula and then equate the real and imaginary parts. First, the term on the right. E to the IP over 5 is cosine of pi over 5 plus I sine of pi over 5. Now the two terms on the left. AE to the IPA over 7 is A times cos of pi over 7 plus I sine of pi over 7. The second term, root 2 BE to the negative I pi over 4, is root 2b times cos of negative pi over 4 plus I sine of negative pi over 4. We know cos of negative pi over 4 is 1 over root 2, and sin is negative 1 over root 2. Now, we substitute everything back into the original equation. We have a cos pi over 7 plus I. A sin pi over 7 plus b minus ib equals cos pi over 5 plus I sin pi over 5. Now we equate the real parts on both sides of the equation. This gives us a cos pi over 7 plus b equals cos pi over 5. Then we equate the imaginary parts. This gives us a sin pi over 7 minus b equals sin pi over 5. We now have a system of two linear equations with two unknowns, a and b. We can solve by addition. Adding the two equations, the b terms cancel. We get a times cos pi over 7 plus sin pi over 7 equals cos pi over 5 plus sin pi over 5. Solving for a, we get the exact value for a. We can then substitute this back into either equation to find b. The exact value of b is sin pi over 5 minus a sin pi over st. Here's a problem involving loci that requires a bit of algebraic manipulation. The question asks us to find the Cartesian equation of the locus of points defined by the equation modulus of z minus 3 equals modulus of z plus I. We've seen that this represents the perpendicular bisector of the line segment connecting the points 3, 0, and 0, 1. Let's prove it algebraically. We'll start by letting z equal x plus y. Substituting this into the left side of the equation, we get the modulus of x minus 3 plus iy. On the right side, we get the modulus of x plus I times y plus 1. The modulus of a complex number a plus bi is the square root of a squared plus b squared. Our equation is now root of x3 2 plus y2 equals root of x2 plus y plus 1 2. Let's expand both sides. Squaring both sides to remove the square roots, we get x3 2 plus y2 equals x2 plus y plus 1 2. Expanding the brackets gives us x2. 6x plus 9 plus y2 equals x2 plus y2 plus 2 plus 1. Now we simplify. Notice that the x squared and y squared terms appear on both sides of the equation. We can cancel them out. We are left with negative 6x plus 9 equals 2y plus 1. Rearranging this equation to solve for y, we get y equals negative 3x plus 4. This is the Cartesian equation of the locus, and it is a straight line, as we predicted. This final problem ties together several concepts we've covered today. It involves converting forms, applying properties of modulus and argument, and solving for a specific condition. The problem asks us to write the number 1 plus root 3i in polar form, and then find all integer values of n for which this number raised to the power of n is purely imaginary. First, let's find the polar form of z equals 1 plus I root 3. The modulus slash z is the square root of 1 squared plus root 3 squared, which is root 4 or 2. The argument is arctan of root 3, which is pi over 3 radians. So z is 2 cis pi over 3. Now for the second part. We want to find in such that z to the n is purely imaginary. Using the properties of polar form, z to the n is 2 to the n cis of n pi over 3. For a number to be purely imaginary, its argument must be a positive or negative odd multiple of pi over 2. So we set our argument and pi over 3 equal to this general form. We can divide by pi to get n over 3 equals 1/2 plus k. Multiplying by 3, we find that n must be of the form 3/2 plus 3k, where k is any integer. However, the problem states that n is an integer. Let's check some values of k. If k is 0, n is 3 to 2, which is not an integer. If k is 1, n is 9 2. If k is 1, n is 3 2. It seems there are no integer values of n. This is a subtle point that sometimes catches students. By carefully checking the conditions, we find that no integer n exists that makes z to the n purely imaginary. Let's work through one more IB-style problem on loci to round out our practice. The problem asks us to sketch on a single Argand diagram the region defined by two inequalities. The modulus of z minus 1 plus I is less than 3, and the real part of z is greater than 1. Let's handle each inequality separately. First, consider the inequality modulus of z minus the quantity 1 minus I is less than 3. The boundary of this region is the equality. Modulus of z minus 1 minus I equals 3. This is the equation of a circle. The center of this circle is the complex number 1 minus I, which is the point, 1, 1. The radius is 3. The less than sign means we shade the region inside the circle. Since the inequality is strict, the circle itself is not included, so we draw it as a dashed line. Now for the second inequality. The second inequality is that the real part of z must be greater than 1. The real part of z is x, so we are looking at all points x, y, where x is greater than 1. The boundary here is the line x equals 1. The greater than sign means we are interested in the region to the right of this line. Again, since the inequality is strict, the line x01 is not included, and we draw it as a dashed line. Now we sketch both regions on the same Argand plane. The solution to the problem is the set of points that satisfy both conditions. This is the intersection of the two regions. The resulting shaded area is the solution to the problem. It's the part of the circle's interior that lies to the right of the vertical line x equals 1. That concludes our in-depth look at complex numbers for the IB Mathematics, Applications and Interpretation Higher Level Curriculum. We've covered a wide range of essential topics today. We started by visualizing complex numbers with the Argand diagram and learned to work with Cartesian form. We then introduced modulus and argument, which are the length and direction of a complex number, and saw how these define the polar and exponential forms. We explored the powerful properties of these forms for multiplication and division, seeing how they simplify these operations into simple scaling and rotation. Finally, we applied these concepts to understand transformations, analyze geometric loci, and even model wave phenomena, solving 5 IB-style practice questions along the way. Understanding these concepts thoroughly will be critical for your IB exams. Remember, practice is key to mastery. If you need further assistance or personalized guidance, please don't hesitate to contact our tutors. Our team of expert tutors is here to help you succeed. Thank you for watching.